Hi everyone. We're about to begin Chapter 5. We begin the chapter with a review of writing linear equations in slope-intercept form. As you might remember, you should remember, that slope-intercept form is y equals mx plus b, where y and x are our variables, m represents the slope, and b represents the y-intercept on the line. There are a few things that Chapter 5 reviews for us, and that is writing an equation of a line when slope is given. So we know that slope is m equals minus 2, and we are given the intercept of b equals 5. It should be very simple for you to remember how to write the equation y equals negative 2x plus 5. In the last chapter, we also practiced writing the equation of a line that was from a given graph. So here you see a graph of a line that runs through 0, negative 4, and 2, 0. We need to determine what the slope is for this line, so we're going to use our slope formula, negative 4 minus 0 over 0 minus 2. Please be sure that you're using the points in the proper order, and this would give us negative 4 over negative 2, which would then equal a positive 2. If we look at the this point here where it's crossing our y-axis, we can see that the b is equal to negative 4. So here I have m equal to 2, b equal to negative 4. It should be a simple jump to making our equation using our slope-intercept form, minus 4. It's also a good thing to note that even though when we're learning how to deal with integers, we often use the plus and negative 4. And I know that I talk a lot about you doing that when you're doing big algebra problems. But when we're looking at slope-intercept form, it's often more simple to just put the subtraction sign there instead of plus and negative. You're at the point now where you should be knowing that they are interchangeable. Okay, so now we're going to use the linear functions to do some linear modeling in order to apply it to real-life situations. So in a linear model, we still use the y equals mx plus b form, where m represents a rate of change, which we've talked about already. But when we looked at rate of change in the last chapter, we did not have an intercept. We had a line that ran through the origin. In linear modeling, there is an intercept, and that is what we will call an initial amount. So we look at where some things in a story will start, and then take a look at the amount of change, or the rate of change, when it can be modeled linearly. So let's take a look at a problem. We have some trout. Here's my fish. And the trout have a population of 44. Whoops, put a decimal in there. Let's start again here. 44.5 thousand. And this is in 1995. So it is projected over the next 10 years that there will be an increase of 3.2 thousand per year. And so what we want to do is write an equation that would model that. Now, the difference between using a linear model is we don't always follow the y equals mx plus b form, even though we are using a linear function. And what I mean by that is, because it's generally a word problem, we usually write the activity that's happening within the word problem. So here we're going to start with the initial amount, which is RB, but I'm going to list it first because that's where our counting of the trout would start. And then I'm going to say that this is going to change by 3.2 thousand per year, where T equals the number of years since 1995. So we can project from 1995 how much trout should have or should be in the pond in any given year over the next 10 years. So this problem asks us how much trout would be in there in 2002. So I want to take the difference of the two because I only want the number of years, right? So the year 2002 minus the 1995 is going to give me the 7 years. That's what T equals. T equals the 7. So if I sub that in, I end up with about 66.9 thousand trout. Okay, so here's a rather poorly drawn graph of the data we were just looking at. And so I plotted my beginning point at 44.5 thousand, and I plotted a point at the year 2002 and 66.9 thousand. And so the idea with linear modeling is, were the change or the increase in the population to remain the same past 1995, we would be able to follow this line and continue to project where the fish should have been. So say I wanted to go to 2006. My line's not quite that straight, but I think you get the picture. This is part of what we're going to be doing. This is called extrapolating the data. So we go a little further than what our data actually proves, and we project that this is where approximately the amounts would end up. So this is what you're going to be practicing in this chapter. I've left an assignment for you to do in class when we get together next. See you tomorrow. Bye.